Okay, now we're going to get started with a method for determining reaction forces for an indeterminate beam and frame, and then we can move on to trusses. Um, Now, up until this point, everything has been determinate, as in we can just use equilibrium, some of the forces, some of the moments to find reactions. But now we have too many reactions and we need to use something else. So by the end of this lecture, you should be able to determine the reactions and subsequently draw shear and moment diagrams for an indeterminate beam and frame using the force or flexibility method. And frame. Yep, I'll go back and add that. So, okay. Now, we're talking about statically indeterminate structures in general. There are advantages to them, such as often when you have something that has a redundant reaction, you will, right, the more support you have, smaller forces and moments are developed within your individual members, within your beams, within your columns, because you have more support, right? That kind of makes sense. Smaller spans, maybe, and that can be a good thing because smaller design moments mean you require a smaller cross section for your design, less concrete, less steel. So it's cheaper, right? Um, Also, adding extra supports means you likely have redundancy in your design, which means you're not going to suddenly collapse. Right. It's always advantageous to not have a sudden collapse, a sudden failure. Disadvantages is that disadvantage. One disadvantage is that you can have, if you have differential settlement, if you have displacements, fabrication errors, temperature, additional stresses, those can all cause additional stresses within your cross section. Whereas if you just have a simply supported beam and one side settles a little bit more, well, okay, it's just rotating the beam a little bit as opposed to now it's pulling two sides of a beam down or one side down, right? Okay. There are multiple methods. I'm going to talk about two specifically for analyzing statically indeterminate beams. If you look in the book, there are some chapters that we have not done regarding calculating displacements, like with conjugate beam or slope deflection. And then there's other ways of analyzing statically indeterminate beams, like moment distribution. And those are all just tools for people to use. I mean, ultimately, we're not going to be doing this by hand. So this is all just making sure that you understand the basics of different methods so that you can understand how computer programs work if you need to use them, right? If you don't understand the theory behind the computer tools that you're using, then you might not be able to use them correctly. So we're going to talk about two different methods. The force and flexibility method, which is what we're going to learn in this class, and then the displacement or stiffness method. And let's first talk about the force flexibility method. Flexibility. Or the The force and flexibility method is one in which you don't know the forces. You don't know reactions. Whereas the displacement method, you don't know displacements. So for example, we don't know reactions, so we're going to look at where we know displacements, which would be at the supports. In the stiffness method, we don't know the displacements, so we're going to look at the displacements of things that are moving as opposed to things that are not moving. So like within frames and stuff, like, you know, the tops of frames that might not be attached to the ground or attached to laterally to something. So because of that, there's often a lot more unknowns with the stiffness method. So what else? The force and flexibility method satisfies compatibility, such as at the support, right? We know that at a support, a displacement has to be a certain thing. So we're being compatible with that. And it also satisfies force displacement requirements, which is what we've been using to solve like virtual work and such, to solve for displacements. And the force displacement requirements are all based on assumptions. So, yeah, the force displacement is your material response to loads. So we have to make assumptions on our material response, such as it's linear elastic. It's not linear elastic. We're sticking with linear elastic, but right. Um, Whereas the displacement or stiffness method satisfies equilibrium. Right, it focuses on forces instead of displacements. If and to satisfy equilibrium, and also the force displacement requirements. The force and flexibility method uses flexibility coefficients. How flexible something is. Whereas the stiffness method uses stiffness coefficients. How resistant to movement it is, right? For the force and flexibility method, once you determine your reactions, you use equilibrium to solve once you determine your reactions, you use equilibrium to solve for all reactions, right? Whereas the displacement method, once you find your displacements, you use those to calculate the forces. And your reactions. So they're kind of backwards from each other. We are going to focus on the force and flexibility method because it's actually fairly straightforward and builds off of everything that we've been doing recently. The displacement or stiffness method is the most used method for computer analysis programs. So if you plan on going into structural engineering or some other type of engineering where you want to do a lot of analysis, you will need to learn the stiffness method so that you understand those computer programs that you use. The stiffness method is also based on, uses linear algebra, which is a class that is not currently in the UALR curriculum for our civil and construction engineering degree. So we're not actually going to be able to go into looking at the stiffness method because you would need to know some linear algebra. So if you are looking to get into structural engineering, I would highly recommend taking linear algebra if you have room in your schedule. And maybe one day we'll be able to teach the stiffness method. If not, you will learn it when you go to graduate school. So all that being said, we're going to focus on the force and flexibility method just so that we have some type of approach to solving statically indeterminate beams and other structures. I should probably make this structures. Right, it's not just beams. Right. Okay, so this is the one we're doing. This is the one that you should know if you want to get into doing a lot of analysis or structural engineering. Okay? Okay, here's the general procedure for the force method and how it happens, right? So let's say we have a beam that has a fixed end on one end and a roller on the other. So let's look at how many reactions that is. All right, we've got our vertical reaction at B, a vertical reaction at A, horizontal reaction at A, and a moment at A. So if we think back to lecture 3 on static and on determinacy, determining determinacy, right? We need to say how many unknown reactions are 1, 2, 3, 4. There are 4 unknown reactions. And how many members? 1 member, 1 beam, right? So that means, if I go back to lecture 3, I have R, and I have to compare it to 3N. 3 meaning our 3 equations of equilibrium. In a coplanar 2D structure, that is the sum of the forces in the X, the sum of the forces in the Y, and the sum of the moments about Z. Those are all equal to 0. And I can have as many equations of equilibrium as I have members of my structure. There's only 1 member. So 4 compared to 3. Uh-oh. I have more reactions than I have equations. That means I am a statically, this is a statically indeterminate beam, indeterminate, and it is 1 degree indeterminate because 4 minus 3 is 1. I have 1 more reaction than I have equations. So if this up here is my actual beam, what I'm going to do is I'm going to take away 1 of my reactions. And I'm going to choose to take away this roller. So now, if I look at my primary beam, that's what this next one is called, I only have the fixed end on the left side. I have a vertical reaction, a horizontal reaction, and my moment at A. And I have my force P. So 1, 2, 3 reactions. All right, this is a statically determinate structure, right? And if I look at the display shape of that, it's going to look something like that. Don't worry, I draw it better on the next slide. And then, to counteract that, I'm going to draw my redundant structure, my redundant beam. My redundant beam. Oh, I'm going to want that to move over a little bit. Right, up here with my actual beam. Now I'm going to have a redundant beam where I take into account that redundant force, that extra force. I'm going to apply By. as a concentrated force at the end where the roller would be. If I look at my reactions, I still only have my 3. So it's still statically determinate, right? 3 equations, 3 unknowns. And if I look at that displaced curve, it looks something like that. So I just broke my beam up, my actual beam, into 2 different beams. The primary beam, in which I take away one of my redundant forces, one of my redundant reactions, but I still am applying my actual loads. And then my redundant beam, where I apply that redundant reaction as a load itself. And what happens when I do that, I get to use that nifty thing called superposition, right? Where I can add together the displacements, I can add together the reactions, I can add together the stresses, moments, all that, of 2 separate loadings on the same structure, provided they meet the 2 limitations of superposition, which are that I have a linear elastic material and that I only have small displacements. Right? So if I look over here, my actual beam, purple, right? I chose blue, red, and purple because red plus blue equals purple. Yep. We're learning about colors today. Right? I still have, I want purple. Here is my beam that has too many reactions. Oh, I don't care about the reactions. I was looking at the wrong sheet. Okay, sorry. Right? This is my displaced shape for my actual structure. That's the second one, the primary structure. That's my displaced shape where I take away that redundant reaction and I get a displacement at B that I'm going to call delta B. And I have my redundant structure where I apply that redundant force to basically counteract, right? You might see where this is going. And I'm going to get delta prime BB. Delta prime BB means displacement at B, that's the first B, displacement at B due to a force or an unknown reaction, right? At B. That's BY. Alright. So displacement at B, that's the first B, due to my unknown reaction at B. That's my second B. And you see, if I add those 2 together, this is where my compatibility comes into play, right? I want my displacement at B plus my displacement at B in the primary structure plus my displacement at B in the redundant structure. In this case, I want them to be equal to 0 because I actually have a support there and it is not allowed to have any displacement in the y direction. So here on the right side, I drew the actual displaced shapes to scale. You can see that this height at the end B is equal and opposite to this height in your primary beam. So when you add them together, you get 0. So if I add these two curves together, I get my actual displaced shape in my actual beam. And I can use that to solve for my unknown reaction at B, and then use that to solve for my other unknown reactions. Right? This compatibility is just saying that right here, right? Displacement at B and displacement at B. I want this to go away. Why are you there? Go away. So ignore this beam. It's not supposed to be there. So I have found, right, my displacement at B due to my unknown reaction at B, and I need to calculate these, right? And my displacement at B in my primary structure with that one redundant force taken away. So what I'm going to use in this case is the linear coefficient. I need to calculate these deflections and then use them to calculate BY. So we're going to use something called the flexibility coefficient, right? The linear flexibility coefficient to find delta prime BB and then ultimately BY, right? So delta prime BB, my deflection at B due to that unknown reaction at B is this flexibility coefficient, which has the same subscripts multiplied by my reaction force BY. FBB is going to measure displacement per unit force. So if it's in displacement per unit force, so inches per kip, millimeters per kilonewton, that's what the FBB would be in. And basically I'm going to use that then go back to my compatibility equation and put that in instead, right? I have my displacement at B in my primary structure, plus now instead of putting delta prime BB, I'm going to put FBB times BY, and that's got to be equal to 0 for my compatibility, right? So what I can do is calculate delta B and FBB and then solve for BY. We're going to go over how to calculate those deflections and that flexibility coefficient, but right, I have one equation, one unknown, my BY. Now, if I can put that back in to my actual beam, right, my unknowns were the BY, AY, AX, and MA. Now, if I know BY, I'm only down to 3 unknowns, and I have 3 equations, 3 unknowns. Right? So we pick a redundant force to draw a redundant structure, solve for that force, and then put that back into the actual beam to solve for the rest of the unknown reaction forces. That's the basic premise of the force or flexibility method. As I said, you can actually use any unknown force or moment as your redundant force. So let's go back to my actual beam, right? This is the same beam. It has 4 unknown reactions. And it is 1 degree indeterminate. So I chose to take away BY, but what if instead I took away that moment? So now if I draw my primary structure, what happens if I take away a moment from a fixed end? Right, it becomes a pin because it can't hold moment. It can only constrain horizontal and vertical movement. So this becomes a pin. This is still a roller. I didn't change anything. Now I have my vertical reaction at BY, my vertical reaction at A, and my horizontal at A. This is a lovely, simply supported beam that we all know how to solve. Right, but I still apply my actual load. For my redundant structure, I have the same redundant. I keep using structure and beam interchangeably. Right, a beam is a type of structure. Sorry if I'm confusing you. Right. So your primary structure and your redundant structure, or your primary beam and your redundant beam, have the same boundary conditions, right? Right. Same supports. So beam has a pin on one side, roller on the other. Still have the same types of reaction forces. So if I take away that moment reaction, what type of motion was the moment constraining? It was constraining rotation. So it needs to be, whereas in the actual beam, right, there's no slope here, and it would deflect like that. Now I'm going to allow a slope, so it's going to displace like that. But I want to add a rotation, right? It's going to have some sort of rotation. A. Well, we're going to look at that in a second. So I don't want it to rotate. I want my redundant structure to prevent that rotation. So my redundant structure is going to apply a moment at A. So that now it's going to look like that. Right? So previously, I took out my vertical reaction at B and applied it as a concentrated load at B. Now I'm taking out my moment at A reaction and applying it as a concentrated moment at A for a pin end. Right? This becomes that. So again, I'm going to look at the display shapes. Here's my primary structure and my redundant structure. My primary structure is going to have some type of rotation at A. And my redundant structure is going to have a similar rotation at A due to a moment at A, right? Rotation at A due to the moment at A. The unknown moment, right? Now, I actually drew the display shape because I thought that was easier to understand than the slopes. But what you notice here, right here, that's where my compatibility is. Where can I write that? Try to figure out where to draw that. I want it to ultimately be a fixed end. So I want my rotation at A from my primary structure plus my rotation at A due to the moment at A in my redundant structure to equal, oops, that needs to be blue. Rotation at A due to a moment at A in my redundant structure to be equal to 0 because it is a fixed end. Right? So again, I'm going to, I don't want this there either. Why are these here? I didn't mean to put them there again. Can I like draw a shape over that? Let me see. No, not at all. Okay. I wonder, actually, can I choose like white? Let me see. That's the one I want the big guns. Yeah. I don't know why that's there. It shouldn't be there. I was all excited that my shapes were finally back. Okay. So, yeah, it kind of looks like giant lips or something. I don't know. So, I want, right, I have my rotation at A in my primary structure, my rotation at A in my redundant structure due to that moment. And now, instead of using the linear flexibility coefficient, I'm going to use the angular flexibility coefficient. If I can learn how to spell coefficient. Right? I'm going to multiply that moment at A times this coefficient, alpha AA. This measures rotation per unit moment. My flexibility coefficient was a nice little script F. My linear flexibility coefficient was a nice little script F. My angular flexibility coefficient is alpha. And again, it has the same subscripts as the redundant structure rotation. Now, if I go back to my compatibility, right? Get rid of this too. I don't know what just happened here. If I go back to my compatibility, I want my rotation at A and my primary structure plus, now instead of the rotation at A due to my unit moment at A, I'm going to put my flexibility coefficient, my angular flexibility coefficient times my moment. And that has to be equal to 0 because I want a fixed end. Right? Again, now we're going to, oh shoot. Now we're going to calculate, before we calculate our displacements, now we're going to calculate our angles and that angular flexibility coefficient. Now I have one equation, one unknown. Solve for that moment. That reduces my reaction forces from 4 down to 3 if I can find the actual moment. And I can use my equations, my 3 equations of equilibrium. So you can use any unknown force or moment as the redundant. It makes a lot more sense maybe to use the, in this case, take out that roller, but maybe you know the displacements for certain structures more than others, or you have them written somewhere. So, but so you can choose anything. Also, finally, how do I know how many redundant structures? Well, it's equal to the degree of indeterminacy. Here we have a single beam with 3 spans, right? Let's write my reaction forces. Vertical at A, B, C, and D. And I also have a horizontal reaction at A. Even though it's probably going to be 0, but, right, I don't have any, I don't have enough. So, my actual beam I have 1, 2, 3, 4, 5 reactions. My N is still equal to 1. There's just one beam, right? Not even attached at B, apparently, if you squint your eyes. It's supposed to be attached at B. So 5 is greater than 3 times 1. Statically indeterminate. 2 degrees, right? 5 minus 3 is 2. That means I need 2 redundant structures. I got away with 1 before, but now I need 2. So I need to remove 2 of my reactions. Well, in this case, it's easy if you just remove the 2 middle ones, because then you get a simply supported beam. And everybody likes simply supported beams, right? So now my primary beam has a pin on one side, a roller on the other, and then it has my 2 forces from my actual beam, right? I have to have 2 redundant beams. So, or 2 redundant structures, whatever I'm calling them at this moment. Redundant beam 1, which has the same supports as the primary beam. It's simply supported, but I'm applying a load BY where I took out that BY in the initial from the actual beam. And I have to have a second beam. My second redundant beam still has the same simply supported ends as the primary beam. And I am applying CY. Right? This has a vertical reaction at A and D, and a horizontal reaction at A. Redundant beam 1 has DY, AY, and AX. The primary beam has DY, AY, and AX, right? So they're all statically determinate, 3 unknowns. I can use my 3 equations. But I had to have the 2 redundant beams because I had 2 degrees of static indeterminacy. And again, I'm going to look at my display shapes, right? My display shape for this one, or display shape for my redundant beam, my first one, and my display shape for my redundant second beam. Don't worry, I drew them with the computer too. They look like that. The actual beam is pretty exaggerated because it was hard to see otherwise. Right. Now I have to look at multiple displacements. I have at B in my primary structure, displacement at B, and a displacement at C. In my redundant structure, I have a displacement at B, displacement at B due to that force at B, but I also have a displacement at C due to that force at B. In my second redundant structure, I have a displacement at B due to the force at C, and a displacement at C due to the force at C. So if I write those down, my displacement, I'm just going to write down the 2 new ones that are kind of confusing looking. My displacement at C due to my force at B, right? Displacement at B due to, displacement at C due to force at B. And my 1 in my structure 2 is delta prime BC. My displacement at B due to my force at C. And then you can see I have to have two compatibility equations. My displacement at B in my primary structure plus my displacement at B in my redundant structure 1, where I applied the force at B, plus my displacement at B, where I applied my force at C from my second redundant structure. And that has to equal 0, right? Right about here. Right, that's equation 1. It's very hard to tell because of the crazy shape or crazy scale that I promised. It's 0. My second compatibility equation happens at C, right? This is B, this is C. My second compatibility equation means my displacement at C plus my displacement at C due to my force at B plus my displacement at C due to my force at C is equal to 0. Make that B look a little bit better. If I take those three, right, those three displaced shapes, the primary structure, the redundant structure 1, and redundant structure 2, and I add them together, I will get the actual displaced shape of the actual beam under these loading conditions, which looks like the purple displaced shape up at the top, if it's really exaggerated. So again, I'm going to use my linear coefficients. Right? If I look at the redundant structure 1, I have a deflection at B due to a force at B. Oh, jeez. And it's equal to that flexibility coefficient with the same subscripts times that force By, because, right, that's a flexibility per unit force. Similarly, my deflection at C due to that force at B is flexibility coefficient with the same subscripts times By, right? If I look at my second structure, I have my deflection at B due to my force at C, and my deflection at C due to my force at C. Deflection at B due to my force in C, FBC times CY. My deflection at C due to that force at C, FCC, CY. And you remember I have my primary structure deflections as well. Deflection at B and my deflection at C. So if I look at my compatibility, I've got my deflection at B in the primary structure plus my deflection at B in the first redundant structure. So that would be, if I replace it with right, deflection at BB. And I also have, right, I need to add these three up. So 1, 2, 3, right? Just sum them down the page. I also have my deflection at B due to my force at C. Times CY. And that has to equal 0. You'll notice they all have the first, right, let's do a little B, B, B. So I'm always looking at my deflection at B. That's what that subscript means. And I don't know, let's pick an orange. My second subscript, B times B. That means force at B, so I multiply by BY. Or my force at C, so multiply by CY. Then I need to go look at my deflection at C plus my flexibility coefficient, FC. Right. The first one needs to be C, the second one can be B because I'm multiplying by BY. My flexibility coefficient at C due to the force at C multiplied by CY equal to 0. Right? Again, C, C, C. All of them are the deflections at C. One of them is in the primary structure, the first one. The second one is the deflection at C due to the force at B. So it needs to be multiplied by B. And the second one is the deflection at C due to the force at C. So multiply by C. Now we calculate delta B, delta C, the primary structure. Guess I could. Right? Delta B, delta C, my flexibility coefficients, FBB, FCB, and my other flexibility coefficients, FBC, FCC. So my only unknowns are my force at BY and my force at CY. So solve for those. I have 2 equations, 2 unknowns. Ta-da! And then after that, you can use those to solve for, right? Once I know BY and CY, I can solve for AY and DY. AX is probably 0. We'll still draw it, but it's 0. Right? So I can take any redundant force as my redundant, I can take any of my reactions as my redundant force and create a redundant structure from it. And the number of redundant structures that I need is based on my degree of indeterminacy. And that's where you start to get into solving multiple equations with multiple unknowns. So that is where you eventually get into using matrices and linear algebra, which is why the stiffness method and the flexibility method are used with with linear algebra. Okay? So that's why you should take it if you want to do this stuff. I wanted to talk about Betty's law. It's Italian, so Betty. I don't know, Betty. Should call my stepmother. She's Italian. So let's say I have 2 different redundant structures where I apply unit loads. If I want to find the deflection, let's pick the right color here. If I want to find the deflection at B due to the unit load at A, right? Deflection at B due to the unit load at A is my flexibility coefficient, FBA, times the load applied, which is 1. If I want to find the deflection at A due to a unit load at B, I find the flexibility coefficient, AB, and I multiply it by the load, 1. Right. This is a unit load at A. This is my unit load at B. Now let's say I was using virtual work to find these deflections. And redundant structure A is my real structure. And B is my virtual structure. I recall back to virtual work. I need to find the internal moments. So I solve for MA, internal moment, in my real structure A, and I solve for MB, which is my internal moment in my virtual structure B. And if I want to find the displacement at B due to A, right? If this is my real structure and I want to find displacement at B due to A, I would apply a unit load at B and find my internal moment, right? guess I should have led with that. But yeah, if I want to find my displacement at B, if like this was my actual real structure, structure A, and it was subjected to a unit load at A, and I wanted to find my deflection at B, I would apply a unit load at B as my virtual structure. So if I wanted to calculate that, it would be the integral of the moment in my real structure, which is MA, and my moment in my virtual structure, which is MB, over EI, and you take the integral, right? My moment in A is my real, my moment at B is my virtual in this case. Now I've just said that my displacement of A is also equal to my flexibility coefficient. So I can say my flexibility coefficient BA is equal to my moment at A, moment at B, EI dx. Alternately, what if my structure B, right? What if this was my real structure? And I wanted to find my deflection at A due to that unit load in my real structure. I'd apply a unit load at A for my virtual structure, right? Now, if I want to find my deflection at A due to that load at B, I take the moment in my real structure, MB, multiply it by my moment in my virtual structure, MA, all over EI dx. Now in this case, my real is my MB and my virtual is my MA. And again, my deflection is actually the flexibility coefficient because I was applying a unit load. So my flexibility in A due to a load at B, a unit load at B, is the integral of MB What do you notice? Due to one of those rules that we learned about arithmetic, MA times MB is equal to MB times MA. Now what's that rule? I don't know. The order doesn't matter. So therefore, FBA is equal to FAB. Right? My flexibility at B due to a unit load at A is equal to my flexibility at A due to a unit load at B. It doesn't matter where A and B are along the length, that's going to be true. That also means if let's say I wanted to find the displacement right? If redundant B was still my real structure, and now I wanted to find my deflection at B due to a load at B, well, I would just apply the virtual load, unit load twice, right? Flexibility at B due to a unit load at B is equal to the integral MB times MB over EI. So you can just square the moment, take the integral to find the displacement or the flexibility coefficient. Okay? So that is all of the theory behind the force method. I'm going to summarize the approach and then we're going to do some examples. So it's nothing you haven't really seen, right? You know how to find reactions of statically determinate structures. Hopefully you've been doing that for a while. We just learned how to find displacements with virtual work or with double integration. And put them together and you can use the force method to solve statically indeterminate beams. So our force method procedure is: first, determine the number of redundant structures required. Right, remember it's equal to your indeterminacy, so R minus 3n is your degree of indeterminacy. And number of redundant structures. I'll write out redundant, because if not, I'm writing red and red. Redundant structures. Right? Draw them. Draw your primary beam, and redundant structures, right? Primary beam is where you take out have removed your redundant forces. Redundant structures is where you apply the redundant forces. Primary, I guess I should say structure here. And remember, all structures have the same boundary conditions. Right? From there, I can write my compatibility equations. where I have displacements or rotations, right? Sum of your displacements or sum of your rotations equal to a known value. Sometimes it's 0, sometimes we're going to have settlement, right? I'll write that in purple. Well, yeah. Sum of your displacements or your sum of your rotations finally, next we're going to determine our deflections in your primary structure and your flexibility coefficients. Which you can use any number of tools. Right? You can use double integration to find your deflections. Virtual work. There are also inside your cover of your book are some solutions, and then there's also Bette's law or theory or method or whatever it was called. Those are just ways to be able to do it. Right? Finally, you calculate your redundant forces. Use equilibrium to solve for the other unknowns. And finally, you can double check all this. Like, that's what you really need to know, and you can double check everything with shear moment functions or diagrams. So that's it. That is the flexibility method. Next, we're going to do some